Welcome to AUT-142 Station number 4, where we'll be going over vehicle heating systems. Learning tasks for this station are going to be 1. To understand and explain the 4 types of commonly found heating systems, 2. Understand and explain the operation of each of those systems, and 3. Perform diagnosis on a conventional heater core system. Safety in this case, we're going to 1. Keep loose hair and clothing away from turning engine components as always, and 2. Know that heaters can, to the surprise of no one, get very hot, so be careful where you place your hands when working around the heating pipes and heater cores. So jumping right in, heater systems. Heating systems are, as one would expect, designed to add heat energy to the interior passenger compartment of the vehicle in order to raise the temperature as compared to a mechanical AC system, which we've been talking up to this point, which is designed to remove heat energy from the cabin. To accomplish this, vehicle heating systems break into 4 major categories. 1, we have conventional heater cores. 2, we have electric grid heaters, sometimes referred to as PTC heaters. 3, we have electric or mixed heater cores. And 4, we have heat pumps. Let's start with the conventional heater core. So the earliest and simplest of all heating systems is the conventional heater core. This system circulates hot engine coolant through a heater core under the dash, then diverts air across the fins of the heater core to blow hot air into the cabin. The heater core functions like the evaporator in the AC system, but instead of getting cold, it gets hot from engine coolant, around 180 to 240 degrees Fahrenheit, depending on what the operating temperature of the engine is. As you can see from the picture, the heater core typically sits inside the dash right next to the evaporator in the same housing, and the two are separated by what we call a blend door. When the driver moves the heat knob or commands more heat from the digital AC controls, the blend door will pivot open and allow the blower motor to push air across the heater core. The more heat is demanded, the greater the blend door moves to allow air across the heater core. At full cold, the blend door will stay fully closed and block the heater core off completely, thus stopping any hot air from getting into the cabin. The blend door is moved either by a simple cable, kind of old school style, or by an electronic actuator attached directly to the door under the dash. If the cable breaks or the actuator fails, the blend door can be stuck partially or fully open, allowing hot air to enter the cabin whenever the coolant gets hot, even when the driver doesn't want it to. What are system strengths and weaknesses of this style? So conventional heater core systems are inexpensive to design, relatively simple in their operation, and they're straightforward to diagnose. However, they are reliant on hot engine coolant to operate, which means the heater will not work until the engine coolant heats up. If it takes 5 to 10 minutes for your engine to hit operating temperature, then that's how long it's going to take before you get any serious heat out of the vents, which can be bothersome for some people. Some modern vehicles, usually hybrids and German luxury vehicles, work around this by having an insulated coolant storage tank that holds hot coolant when the vehicle is shut off and parked. The insulated storage container will keep coolant hot for over 48 hours so that when the driver hops back into the vehicle and starts it up, an electronic pump can push hot coolant back into the engine and the heater core, instantly warming the engine up and providing heat for the driver. As you can see from my picture here, we have our coolant heat storage tank. So this is that insulated tank that has pumps and valves so we can move fluid into it. This is where it's going to get pumped. So when you turn the key off on like a hybrid vehicle like a Prius, it's going to pump hot coolant into the storage tank, hold it there, keep it hot for at least a solid 48 hours. And then when you hop back in, it's going to dump that coolant back in, make everything warm again. What are common issues with this style of system? So the most common issue with a conventional heater core system are coolant leaks and blend door failures. Conventional heater core systems, especially with insulated storage tanks, have a large number of cooling hoses and hose clamps, all of which prove trouble spots for leaks, especially as the vehicle ages. Second most common to this is blend door actuator failures. They're extremely common on domestic trucks and cars, which will freeze the blend door in place and cause hot air to be pumped into the cabin, even when max AC is selected and the driver wants only cold air. As a quick aside, diagnostic pro tip, if you suspect the blend door actuator is sticking open, a simple trick is to take a pair of hose clamp pliers and squeeze off one of the coolant hoses going into the heater core. If the vent temperature drops, then you know the blend door isn't fully seated shut, because when we clamp down on that hose, we're stopping coolant from going to the heater core, but if the blend door is closed, that shouldn't matter. So if we actually clamp that line and temperature drops at the vents, we know there's something wrong with that blend door. Next up are electric grid heaters, known as positive temperature coefficient heaters. So electric grid heaters, typically called PTC, positive temperature coefficient heaters, utilize electricity pushed across ceramic resistors to generate heat. Essentially, a specialized controller, a module, sends 12 volts to 240 volts of electricity through the ceramic rods attached to the module. Ceramic is a resistor, so as current flows through it, it eats up the voltage and converts that voltage into heat. The PTC heater is placed under the dash, typically where a heater core would be, and the blower motor pushes air across to the fins of the PTC heater to warm up the cabin. So you see in my picture, you see the PTC heater is there under the dash, has a blower motor. We're very familiar with this by now. All it's essentially doing is replacing a conventional heater core with an electric one. System strengths and weaknesses. A PTC heater has the advantage of not utilizing any engine coolant. This makes it possible for PTC heaters to be used on fully electric and hybrid electric vehicles, which is where they're typically found. A PTC heater can begin heating the cabin instantly and can even heat a hybrid vehicle without having to turn the gas engine on, allowing, on some models, for the driver to command the heater on remotely through a phone app so that the cabin is warm before they even step out of their front door. That said, a PTC heater puts out less heat energy per minute than a conventional heater core system, i.e. less BTUs. So it takes longer for a PTC heater to warm up a cabin as compared to a traditional heater core with hot engine coolant already flowing through it. This system also utilizes a large amount of battery power on hybrid electric vehicles, forcing the range on certain EVs and hybrids to be shortened depending on how much the PTC heater is used. This is in stark contrast to a conventional heater core system, which is essentially using waste heat from the coolant in the engine to warm the cabin, which means that running the heater on a conventional system isn't wasting any energy at all versus the electrical system, which is going to be taxed by the use of a PTC heater. What are common issues with this system? The most common issue that plagues a lot of PTC heaters is cracking or overheating due to the constant heat cycling, going from hot to cold, of the heating rods and the fins. Remember, as things heat up, they expand, and as they cool, they contract. The more heat energy, the greater the expansion. The greater the cold, the greater the contraction. Over time, this expansion and contraction can crack or break the rods and fins of the heater, which often causes the internal circuitry of the controller to get fried. Remember, these units are sometimes pushing over 240 volts, so a quick short at that level of voltage can destroy a lot of electronics. These types of PTC heater failures happen far more often in climates of extreme cold, 32 degrees Fahrenheit or below, due to the extreme differences of heat in the PTC cycles through, while places like Arizona tend to see far less PTC heater failures thanks to the comparably milder climates. Manufacturers are trying to build PTC heaters to be more durable in vehicle applications, but for the last 10 years or so, about 2012 to 2022, they haven't exactly had a stellar track record of reliability, especially in very cold climates. Next up is electric or mixed heater cores. So electric heater cores utilize a high voltage PTC heater to heat up coolant before pushing the coolant into the heater core that's placed under the dash. Designs vary, but generally they will appear like the images shown to the right on screen. It's a simple box that has an internal PTC will heat the coolant and an external electric pump will circulate the coolant to the heater core, making this essentially a fusion of a PTC and conventional heater core system. Some designs have the PTC heater attached directly to the outside of the conventional heater core, as I show here on the right. In this system, the combustion engine is still primarily used to heat the coolant, but the PTC heater can be turned on when the engine is cold in order to provide quick heat to the conventional heater core, allowing the driver to feel warmth out of the vents even when the engine hasn't fully heated up yet. When the engine coolant temperature reaches a certain point, the PTC heater turns off and hot coolant is used 100% of the time to warm the cabin of the vehicle. What are the system strengths and weaknesses? So the great strength of heating the coolant and then using it to warm the passenger compartment is that you decrease the load on the PTC heater, as compared to a system that uses only a PTC heater to warm the cabin. The PTC heater doesn't have to work as hard to warm liquid as it does air, which means this system pulls far less amperage and avoids a large amount of the heat strain that tends to degrade and break 100% PTC style heating systems. This also has the advantage of a fully electric vehicle being able to have a conventional style heater core even without the presence of a combustion engine, given that the PTC heater is warming the coolant, so no internal combustion engine is needed. The weakness of this system is that it has more working parts than either a conventional heater core system or a purely PTC style heater. More parts means more parts to break over time and the added complexity in the system's operation. That said, these systems do tend to hold up pretty well and tend to incorporate the strengths of both systems without many of their weaknesses. What are common issues? Since this is a hybrid of two separate systems, we run into a hybrid of their issues. Leaks are still a major concern, as is the failure of the low voltage pumps and the possibility of the PTC heater malfunctioning. It must be stressed that electric heater core systems have a lot more coolant hoses, connections, and valves than a conventional heater core system, all of which are prone to leaking over time. Being well versed in using a pressure tester and spotting leaks will go a long way when dealing with these kinds of systems. Let me give you an example. So pictured below is the front trunk of a Tesla Model 3. To highlight just how many trouble spots there are, I've placed arrows at most of the junctions and valves of the heater system where leaks are likely to occur. That's a whole lot of places to leak. So if you pause it, take a look at this image, you can see all the lines that run for that heater system. All of these can leak. Those hose clamps can leak, those valves can go bad, those diverter valves can clog up. There's a lot of places where a lot of problems can pop up in this style of system. Next up are heat pumps. So heat pumps are conventional mechanical AC systems with the condenser and the evaporation locations swapped. No, seriously, that's exactly what they are. Same parts, same mode of operation, same refrigerant, we just reverse the flow of the refrigerant. With our standard AC systems, the condenser, where the heat is dumped, sits in front of the vehicle, and the evaporator, the part that gets cold, sits under the dash. If you run the system in reverse, then the evaporator under the dash becomes the condenser. It will get hot, while the condenser at the front of the vehicle becomes the evaporator. It will get cold. Heat is then transferred from outside the vehicle and placed inside the vehicle, making it the exact opposite of a conventional AC system. So what are the strengths and weaknesses of this system? The strengths of the heat pump is that it moves a ton of heat extremely fast, even under extremely cold conditions. A heat pump can be turned on instantly, so no waiting for the coolant to heat up. It moves approximately 300% more units of energy per watt of electrical power used than a PTC heater in most conditions, even when it gets to negative 32 degrees Fahrenheit outside. Put in layman's terms, a heat pump is 300% more efficient than a comparable PTC heater. These systems also utilize fully electric variable compressors, allowing them to be turned on even when the vehicle is parked, so the vehicle can be warmed with the press of a button on your phone, much like a conventional PTC system, just faster. The weakness of the system is in its complexity and how harsh cold weather is on this system. Compared to a PTC and a conventional heater core system, this is easily the most complicated, with the most moving parts and ways to fail. And much like the PTC heaters, a heat pump is placed under an intense amount of stress the colder it gets outside. So using a heat pump system in Alaska or Maine is going to cause a lot of system fatigue, but far less in temperate climates like Arizona. What are the common issues of a heat pump? So heat pumps are plagued by any and all issues that affect the AC system: low refrigerant, improper airflow across the condenser, etc. Everything you've learned in your other stations about AC systems will apply to heat pumps, from pressure tests, performance tests, etc. You'll simply be dealing with heat increases as opposed to heat decreases. All right, we made it to the hands-on section. So for this one, I'm going to show you some simple diagnostic steps for a conventional heater core system. So that would be the one that has the coolant going in it from the engine. It's going to break into three simple parts. One, I'm going to show you how to do a leak test. So again, leaks are the biggest thing, so we're going to check that first with a pressure test. Two, I'm going to show you how to check heater input versus output to see if there's a clog. So we're going to check heat into the heater core and then heat versus out to see if there's a change. That's going to let us know if there's a clog inside there. And then three, we're going to hook up a scan tool. I'm going to show you how we can do some special test functions in the scan tool to see if the blend doors are working right and how to reprogram a blend door. So here we go. We're going to start by removing the coolant pressure cap. So go ahead and unscrew that and take a close look at that cap where it says 20 psi, which is what the system pressure is and what we're going to pressurize it to. So with the cap out of the way, you're going to put your adapter on. Just screws on tight. Make sure it goes on by hand, no tools. Tighten it till it seats all the way down so the gasket is set. Then go ahead and grab your pressure tester. I'm going to slow it down and zoom in here. When you install the pressure tester, you're going to make sure the wing nut is in line with those ridges. So you're going to turn the wing nut so it pops up on those ridges. Now it's ready to be installed. From here, you're just going to take it to the adapter. I'm going to zoom in again. You're just going to rotate it, keep rotating until it stops. Like righty-tighty, it should stop. Once it stops, then you're going to turn the wing nut, turn that perpendicular, and bam, now it's sealed. From here, you're going to take the pump, pump it to 20 psi, which is what the rating was on the cap. So you're going to go off the gauge on the tester, raise it to 20 psi. Once you get there, go ahead and set your pressure tester down, grab a flashlight, and now we're going to look at the lines going into the heater core, which are right back here, and we're looking for any types of leaks at the connection where it goes in. Also, we want to check inside the passenger compartment to see if there's any coolant leaking here. Is the floor wet? Does it smell like coolant, etc.? Because if it's going to leak, that's where it's going to leak. Once you've done this, you're going to go to lab staff. You're going to have them sign off, show them that you have the pressure tester installed, that it's set to 20 psi, and let them know you don't have any leaks unless you do. And if you find leaks, go ahead and point those out, and then we'll sign off on your paperwork. From here, we need to remove the pressure tester. And to do this, you're going to very, very slowly turn that wing nut up to those ridges, and I mean slowly. Otherwise, this pressure is so high, it's going to blow all that coolant out of that tank. So turn that wing nut very, very carefully clockwise up into those ridges, and that way you will release the pressure and everything will be daijobu. So don't worry about it. Turn it slow, you'll be fine. Make sure you clean it up, clean up any messes you make. Go ahead and take off the adapter and put the cap back on. The cap will seal all the way tight, so righty-tighty, you'll feel it, snug, good to go. For this next section, you're going to need to grab a DVOM and a temperature probe from the toolbox. So you know what the DVOM looks like by now, but this is what the temperature probe looks like. You're going to snag that out of the toolbox along with the adapter that comes with it, because you're going to need this to check the temperature going into and out of the heater core. From here, I'm going to have you set up your DVOM for the temperature probe, and the adapter is going to have a positive and a negative on it. You need to make sure the negative goes in the COM jack and the positive goes into the temperature jack. You're also going to have a positive and negative on the temp probe itself. Make sure you align those correctly. From there, you're just going to spin your DVOM to temp, and it should read in Fahrenheit, so about 78.6 for me. The temperature probe has 2 springs on it. Whenever you want to measure the temperature, touch it to something. It's a contact probe. If yours has this little cap on the end of it, make sure you remove that cap first to get a proper reading. Next up, I'm going to have you install the exhaust to this vehicle. I'm going to have you start the engine, and then I'm going to have you run it till it hits operating temperature. Operating temperature for this Duramax is going to be at least the first line on your temperature gauge, so above the 160 going to the bare minimum to the first line. This is going to take a couple of minutes, so what you can do is hop in with the engine on. You can rev it up to about 1500 RPMs. Don't go any higher. That's going to help build up heat faster. So start the engine, run it till it hits at least that first mark, and then we're going to move on. Once we're at a proper operating temperature, I'm going to open my hood. Yours is probably already open. With my hood open, I'm going to set my DVOM to temperature Fahrenheit, and I'm going to check those 2 lines in the back one at a time. So I'm going to touch and record what that measurement is. So I'm trying to get my test probe flat against that black coolant hose, and I'm getting about 126, 127. At this point, I'm like, I don't know if my contact is quite right. So I mix it up, change my contact, get about 136 on one line, and I'm getting about 138, 136 on the other. I go back and forth, making sure that I contact and I get good measurements on it just to be sure, make sure my readings aren't wrong. Go back and forth and record each one that you're going to get. They should be close to the same. They shouldn't have much difference between them if you're doing it right. What we're looking for on this test is with the blower motor off, there shouldn't be more than a 30-degree Fahrenheit difference between each hose, and 30's being incredibly generous. Both the hoses should be relatively the same, because what should be happening is the water pump is pumping coolant through one line, through the heater core, and then out the other. With the blower motor off, there should be no air going across the heater core to pull any heat out of that heater core. If you measure 160 on one hose and you measure 100 on the other, with the blower motor off, that means that that heater core is plugged up. It's trying to push coolant through, but coolant is moving very slowly through the heater core. So again, we're looking for no more, at max, a 30-degree difference between each hose with the blower motor off. Okay, so that's how we're going to do an easy check for a clog in the heater core. Last but not least, I'm going to have you grab one of the OTC scanners, either the Encore or the Evolve, from the toolbox and bring it over to the truck, because now we're going to plug that baby in and we're going to do some actuator checks. Once you've got your scan tool in hand, go ahead and hop on over to the truck and plug it into the data link connector under the dash. Again, silver tab faces towards the engine. It should plug right in, bam, like that. Make sure you have your key in. Make sure that the engine is running and that we're at operating temperature. With your scan tool on, you should see this home screen, and we're going to start by selecting vehicle. So select vehicle and then click auto ID. This will allow it to automatically identify the Colorado you're working on. It should come up with this. Once you see it, select it because that's the vehicle we're working on. From the main menu, click on Special Tests because that's where we need to go to run Special Tests. And you want the HVAC controller, so select Climate HVAC, and it's going to bring you up to the screen for Climate HVAC. It'll show you a bunch of options once you get there, just like this. For now, we're going to scroll to the bottom because we want to access the blend door. So we want the left temperature door motor control direction. Keep in mind that this is going to load up and give us the option to switch between hot and cold with the blend door from the actual scan tool. Before we do that, we need to make sure that we have the AC on, that we set it to maximum cold, and that the blower speed is at max. So AC on, max blower speed, and set the temperature manually on the dial to maximum cold. You should feel it coming pretty darn cold out of those vents before we start this test. Once that's all set up, you're going to come back to your scan tool. You're going to select hot. So when you select the hot option, you should slowly feel the temperature inside the vehicle warm up because the blend door is going to be turning, and it should turn all the way and let hot air into the vehicle. Once you've done that, select cold, and you should feel it stop being so warm and move back towards being cold again. This is a simple test to let you know if the blend door is moving correctly. We are forcing the computer to command the blend door to change, so we should feel that temperature change as the blend door goes through its sweep and then moves back. If we don't feel that temperature change, there's something wrong with the blend door, there's something wrong with its connector. We know it's not clogged, and we know there's not a leak because we already checked that. So this is just a nice, easy way to check to see if the blend door can be commanded to move properly and if it actually moves when it's being told to. Once you've done your blend door check, I'm going to have you turn the engine off because you don't want it running for the next segment of tests that we're going to do. So at this point, again, engine off, but make sure the key is in the run position. So engine off, key in run position. That means the dash lights will still be on, but the engine will be off. For this last segment, I'm going to have you go through a blend door actuator relearn procedure. So on some vehicles, particularly GMs, the blend door needs to be indexed by the HVAC module itself. And what I mean by index is that the HVAC module needs to learn where full open and full closed are for that blend door when we install a new one. The actuators on the GMs can rotate 360 degrees around, but we don't need them to move that far. We just need them to go full open and full closed. And the module can only learn that if we force it to relearn that procedure. Not all actuators need a relearn procedure. The one I'm showing you on screen is from a Ford, and this has index marks on it, so there is no module-based relearn procedure for that particular Ford because it will bump into those marks. But for the GM, again, it rotates 360 degrees. If we don't go through the relearn procedure, we might not get the blend door to open properly. So if we do a blend door test and we're not getting proper heat to come left and right from hot to cold, we may need to do a relearn procedure just to make sure that that indexes properly. So heading back to our scan tool, we're going to exit out of that motor direction test we were just in so we can get to the relearn. So we're back to the special test. Go up to HVAC actuators learns. Go ahead and click on that. It's going to initiate, so make sure our ignition is on, and then we're going to hit continue. From here, we're going to just wait and watch the procedure occur. While this is happening, you should be able to hear the actuators moving behind this glove box. So put your ear over there, you should hear it. Once it's done, it's going to have you turn ignition off then on, so cycle off then on, and then hit continue with the key in the run position. Once you get this screen, you're going to stop, show lab staff, and get a sign-off for completing that actuator relearn procedure. Once you've got that sign-off, you're going to continue through this screen. It's going to dump you back to the special test. Then just hit the back button all the way to the system main menu. You're going to know you're at the main menu when it wants you to clear the current vehicle. You're going to select OK. Make sure you do this before you disconnect the scan tool, and you're golden. All right, you finished up your hands-on, so let's do the summary and get on out of here. So 1, conventional heater core systems utilize hot engine coolant to warm the passenger compartment. 2, PTC heaters use high voltage electricity pushed through a heater grid to warm the passenger compartment. 3. Electric heater cores use a PTC heater to warm the coolant before pumping it into a conventional heater core to warm the passenger compartment. 4. Hot Pockets use microwaves to turn synthetic cheese into liquid magma in only 2 minutes flat.
Will it burn my mouth? It'll destroy your mouth. Everything will taste like rubber for a month. All of the Hot Pocket.
Number 5. Heat pumps are mechanical AC systems, just with the evaporator and the condenser reversed. And there you go. You've survived another lab. You've made it through, and you're probably a whole heck of a lot smarter. At least I sure as heck hope that you are. As always, make sure you clean up your area and put your tools away so you can get that last signature, especially if you made a mess with the coolant, which, I totally know you didn't make because you were perfect and followed every single direction I gave you. And you're already a master mechanic with dozens of years of experience. Of course, you didn't make a mess. But if you did, make sure you clean it up, get those signatures, and then we'll see you at the next station.